Hello, everyone. My name is Shen. I'm an assistant professor at the Department of ECS at the University of California, Irvine. Today, it's my great pleasure to present our work on personalized graph-aided online federated model selection. This is joint work with my PhD student, Puyagari. Federated model selection copes with a problem where there's a server with comparably large capacity to store many pre-trained models. And then a group of learners, also known as clients, are trying to communicate with the server to query models for their learning tasks. And the server sends a subset of models to each client. And then the clients perform learning tasks and return feedback. The chosen subset of models can be fed into each client's memory. There are several challenges, since we are always faced with sheer volume of data, which does not allow us to store and process data at a batch. And the clients may also face with real-time decision-making. In addition, there is no prior information on the performance of the models. And the clients may have limited memory and may perform different learning tasks and require different subset of models at each learning round. So the question is how to perform online model selection with a large dictionary of models beyond client storage capacity. Our approach is that we let the server store a large number of models, and then at each learning round, it picks a personalized subset of models and send to each client. Then the clients perform learning tasks and return feedback for future subset selection. So here comes our graph-assisted federated model selection, where at each learning round, the server constructs a directed graph among models based on historical feedback from clients, which may look like this, where K denotes the number of models in the server. And the directed edges are generated based on historical feedback collected from the clients. Then at each learning round, the server selects a subset of models for each client based on the client's historical feedback and the graph structure. The chosen subset for each client can be fed into its own memory. Upon receiving the subset of models, the client will select a model among the received ones to perform the learning task. And then it sends back only the incurred loss to the server. Such schemes is communication efficient in the sense that each client sends only one parameter, which is the incurred loss, per learning round to the server. And it is also personalized in the sense that each client receives a personalized set of models based on its feedback and memory requirements, also known as budget. This scheme entails online learning and updating schemes, where the server employs received information or feedback from clients to update the graph. Based on the graph, the server chooses a time-varying subset of models for each client. The clients exploit observed loss to update its own criterion to choose model for its own learning task at hand. Since it's an online scheme, we also provide a regret analysis. And we show that each client achieves a sublinear regret. So the take-home message is that all clients converge to the optimal offline model selection scheme. We carry out experiments on real data sets and on two learning tasks, energy consumption prediction and image classification. We compare with non-federated online model selection, where each client stores a set of models and perform online model selection, and the FedaBoost, which is ensemble federated learning approach. Our data set is the energy data set, and there are 50 clients with limited memories, also known as budget. And the models are 20 feed-forward neural networks with different architectures. Here's a budget violation is a percentage of learning rounds where instantaneous budget constraint is violated. Note that FedaBoost is designed such that the expected budget is satisfied, so there's still a certain amount of budget violation. And it can be seen that our graph-assisted online federated model selection achieves the best MSE, and it does not incur any instantaneous budget violation. We also perform image classification tasks, where there are 20 CNNs with different architectures. In addition, the CNNs are trained based on heterogeneous data with unbalanced class, such that the observed CNN perform better in certain tasks. And the clients also have heterogeneous data, which are biased towards certain class. And it can be seen that, again, our graph-assisted online federated model selection achieves the best accuracy and with no budget violation. For more details, please check our preprint that can be found in this website. And please also contact me if you have any feedback or questions. Thank you again.